Hello students, today we are going to start the new chapter, Solutions. So let's get started. In our daily life, we usually come across a variety of substances which are mixtures of two or more substances, isn't it? So solution is one of the most important classes of mixtures which is homogeneous in composition and properties. Okay? It is homogeneous in composition and properties. Now the utility or importance of solution in our life, it depends on the composition. For example, let's say that 1 parts per million of fluoride ions in water, it prevents tooth decay, while when you increase the concentration to 1.5 parts per million, it causes the tooth to become mottled, and very high concentration of fluoride ions can be poisonous. For example, sodium fluoride. This is used if used in higher concentration, it is used for rat poisoning. Okay, so in this chapter we will discuss about different types of solution and the associated laws and the concentration related terms. We will also discuss about solubility, vapor pressure of liquid solution, and colligative properties and determination of molar mass. Okay, so let's start. So what is solution? Solutions are homogeneous mixtures of two or more substances, okay, and whose composition can be varied within certain limits. Now the term homogeneous, it means that the composition and properties are uniform throughout the mixture. Okay, for example, when you dissolve salt or sugar in water, okay, just say salt, after some constant stirring, when you stir this, after some constant stirring, you will not see any salt particle undissolved, or at the bottom or swirling around. So this is an example of homogeneous mixtures. That is, the components are mixed uniformly. Now in such a mixture, now I am repeating this term, components of mixture. So what is this component of mixture? Let's understand this. The components of mixtures is nothing but the substances by which the mixture is made. So basically the solution is made up of two components. First one is the solute and the other one is the solvent. Now in such a mixture, the component that is present in largest quantity, it is known as the solvent. So in the previous example, the water was the solvent and the solute is one or more components which are present in the solution other than the solvent, it is the solute. You can say that it is present in less quantity. So the salt was an example of solute. Okay, this was the introduction part. Now let's moving on and let's discuss about the characteristics of solution. You should know about all these things before getting into the topic, because these are the introduction part. So let's talk about the characteristics of solution. So you already you must be knowing all these things, but still just a revision. The first characteristic is a solution is a single phase system. A solution is a single phase system. Okay, now what is this phase? This phase is a distinct and you can say the homogeneous state, with no visible boundary separating it into parts. For example, if we take water and alcohol, if we mix alcohol and water here, when you mix these two components, when you mix these two, regardless of the relative amounts that you see, they are fully miscible. Okay, the resulting mixture has only one phase, that is the solution, isn't it? There are no phase or you can say a boundary which is separating alcohol and water. ऐसे तो कुछ नहीं दिख रहा है हमें. So when we mix water and oil, ठीक है, this is water and this is oil. When you mix water and oil, they are normally immiscible, isn't it? And their boundary of separation is visible. So they form a two-phase system. They form a two-phase system. Okay. Now, the second characteristic. The second characteristics of solution is a solution does not allow a beam of light to scatter. All right. Solution does not allow a beam of light to scatter. Okay. So we know that light passes from a true solution and is not reflected by the particles of the true solution. That is, the Tyndall effect cannot be seen. The third characteristics is that the particles of solute in solution cannot be seen with a naked eye. This is clear. Then fourth is that a solution is stable and the solute from the solution cannot be separated by filtration process. All right. However, evaporation, you can use evaporation or distillation. All right. Then fifth characteristic is that the solute particles in a solution, they do not settle down. They do not settle down. All right. So these were the characteristics of solution. Now let's move on to the classification of solution. Classification of solution. Classification of solution. That is how the solution is classified. All right. So solutions are classified on different bases. All right. Now on the basis of solvent, first let's see the classification on the basis of solvent. Okay. So on the basis of solvent, the solution may be of following types. First one is aqueous solution. First one is aqueous solution. When solute is dissolved in water, all right, when we take the solvent as water, this is the aqueous solution. All right. For example, ethanol in water. Okay. And second is non-aqueous solution. Non-aqueous solution. So when we take the solvent, something other than water, this is non-aqueous solution. All right. For example, iodine in alcohol. The alcohol is the solvent we have taken. All right. So this is on the basis of solvent. Now the next one is on the basis of number of components. Right. On the basis of number of components. On the basis of number of components. So on the basis of number of components, solution may be classified into binary solution, ternary solutions, quaternary solution, etc. When the number of components is 2, it is known as binary solution. That is, if we take one solute and one solvent, it is known as binary solution. Ternary solution is when the number of components is 3. That is 2 solutes or 1 solvent, isn't it? समझ आ रहा है? So that is ternary solution. Quaternary is when the number of components is 2. just say for example 2 solute, 2 solutes, 2 solvent, all right, or vice versa. So on the basis of number of components, we classify solutions as binary, ternary and quaternary. All right, moving on. So on the basis of, after that, the third type of classification is on the basis of physical state of components. On the basis of physical state of components. So what does this mean? See, on the basis of the physical state of component, the physical state means the physical state in which the solution exists is determined by the state of the solvent. All right. For example, if we are taking solid solutions, here the solute can either be a gas, liquid or solid. But as it is the solid solution, the solvent will be solid. The solvent will be solid. Okay. Now, liquid solutions. And again, liquid solution, the solvent, this is the solvent, all right. This is the solvent, this is the solute. This is the solute and this is the solvent we are talking about. So some examples, let me first discuss this, that in liquid solutions also the solute can again either be a gas, liquid or solid, but the solvent will be liquid. Okay. Then again in gaseous solutions, the solute can either be a gas, liquid and solid, but the solvent will be gas. Okay. So some examples of gas solid mixtures is hydrogen and palladium. Okay. Some examples of liquid solid solution is mercury with sodium forming an amalgam. Some examples of solid mixtures are alloys like bronze and many others when mixed together. Okay. Then in liquid solution, some examples of gas liquid solution is oxygen in water, aerated drinks, carbon dioxide in water. Then liquid solution, alcoholic beverage are basically they are solutions of ethanol in water. Then solid liquid, sucrose or salt in water. Then examples of gas solution, air, which is mostly a mixture of nitrogen and oxygen gases. Then liquid gaseous mixture, the chloroform mixed with nitrogen gas. Then again next example can be the humidity in air. Okay. Then solid gas mixture is camphor and nitrogen gas, dust or smoke. These can be the example of solid gas mixtures. Okay. So this was all about the classification of solution. All right. Now moving on. The next part that we have to discuss is expressing the concentration of solution. Okay. Expressing the concentration of solution. How do we express the concentration? So now composition of a solution can be described by expressing its concentration. The concentration of solution, how do we define it? It may be defined as the amount of solute, which is present in a given quantity or amount of solution. Amount of solute present in given quantity of solution. This is how concentration is defined. Now it can be expressed either, the concentration can be expressed either qualitatively or quantitatively. Either qualitatively or quantitatively. Now if we are talking about that, we are expressing the concentration in qualitatively, that is we can say that the solution can either be dilute, that is very relatively small amount of solute is added, or concentrated, that is very large amount of solute is added. When we are talking about the quantitative determination, that is the amount of concentration of an analyte, it can be estimated or expressed as a numerical value in appropriate units. That is how we determine it quantitatively. All right. Okay. So now, for example, if you have 1 liter of solution, okay, you have a solution of 1 liter, all right, and you have mixed say 10 grams of salt, all right. So now we can say that what is the concentration? We will say it as 10 gram in 1000 milliliters. Okay, so this is how we say it. Now the unit of concentration is moles per liter. We will write it like this: the unit of concentration is moles per liter. All right. Now there are several methods by which we can describe the concentration of solution. There are several methods. What are these methods? Let's discuss. Okay, so what are the method? First is mass percentage. The first method is mass percentage. Okay, denote it like this: W by W. So here the mass percentage of a component in a given solution is the mass of component in 100 gram of solution. Okay, so this is how you can calculate. If we are calculating the mass percentage of a component, it will be the mass of component by total mass in solution into 100. All right, this is how you will calculate. So if WB, let's say WB be the mass of solute B and WA be the mass of solvent A, in that case, how will you calculate mass percentage? It will be like this: mass percentage is equal to WB divided by mass of component. If you are trying to calculate the mass of component B, so it will be WB divided by total mass, WB plus WA into 100. Okay. Now for example, if a 10% glucose solution in water, if you have 10% glucose solution in water, it means that 10 gram of glucose is dissolved in 90 gram of water. Okay, 10 gram of glucose dissolved in 90 gram of water, which results in 100 gram of solution. Okay, so this is how you calculate the mass percentage. All right, moving on. The next concentration term which will be used very much here is the volume percentage. Volume percentage. Okay, V by V. So the volume percentage is the volume of component per 100 parts by volume of solution. Okay, so volume percentage is equal to volume of component divided by total volume of solution into 100. Okay, so volume percentage is volume of component divided by total volume of solution into 100. Now the solution which contains liquid, they are commonly expressed in volume percentage. Okay, now for example, if we say that 100 milliliter of 35% V by V solution of ethylene glycol it contains, how much will it contain? It will contain 35 milliliter of ethylene glycol and 65 milliliter of water. Okay, so this solution, 35 milliliter of ethylene glycol and 65 milliliter of water, this solution is used as an antifreeze in cars, okay, for proper working of the engine during cold weather. At this concentration, this antifreeze, it lowers the freezing point of water, okay, to minus 17.6 degree centigrade. Alright, so this was all about volume percentage. After that, the next concentration term that we have to study is parts per million. Okay, parts per million, ppm. So when a solute which is present in, trace quantities, the concentration is expressed in parts per million. When solute is present in trace quantity, trace means very little amount, trace quantity, the solution is expressed in parts per million. So parts per million, how do we write this? It is number of parts of component, divided by total number of parts of all the components of solutions, into 10 to the power 6. Alright, so now in other words we can say that this is a way of expressing very dilute concentration of substance. Just like percent means out of 100, isn't it? Percent means out of 100. So parts per million means out of a million. So it usually describes concentration of something in water or soil or gas. Alright, so for say just 1 parts per million, 1 ppm, it is equivalent to 1 milligram of something per liters of water. Alright, 1 milligram of something per liters of water. So the concentration of pollutants in water or atmosphere is often expressed in terms of parts per million. Okay, now parts per million is also something which is equal to per kg. Alright, 1 parts per million is also equivalent to 1 milligram of something per kg. Okay, so when gas is dissolved in water, it is expressed in this type, that is 1 in milligram per kg or parts per million. Alright, okay, now after that we have 2 more concentration terms left. The next one, 3 more concentration terms left, that is mole fraction, denoted by this zeta. Now what is mole fraction? Mole fraction is the ratio of number of moles of one component to the total number of moles of all the component which is present in the solution. Okay, so mole fraction is number of moles of the component divided by total number of moles of all the components. So if you have to calculate the mole fraction of solute, you will calculate like this: mole fraction of solute is equal to number of moles of solute by number of moles of solute plus number of moles of solvent. Okay, similarly if you have to calculate the mole fraction of solvent, you will write it like this: mole fraction of solvent, a number of moles of solvent divided by number of moles of solute plus number of moles of solvent. Okay, now in binary solution in this solution chapter we will basically talk about binary solutions. All right, in binary solution, if the number of moles of A and B are Na and Nb, then the mole fraction will be like this. Number of mole fraction of, just suppose A, if we are taking the solute as A and solvent as B, then number of moles of A is equal to number of moles of A, mole fraction of A is equal to number of moles of A divided by number of moles of A and number of moles of B. Similarly, mole fraction of solute, that is B, is equal to number of moles of B divided by number of moles of A plus number of moles of B. Okay, one more thing that we have to consider here, that the number of the mole fraction of A plus mole fraction of B will always be equal to 1. Unity. Okay, mole fraction, it is independent of temperature, and it is also a dimensionless quantity. Okay, will not write any units here. So just say that if we have a solution containing I number of components, all right, if we have a solution containing I number of components, so in that case the mole fraction will be written as, how will you write the mole fraction? It will be like this: mole fraction of I is equal to number of moles of I divided by N1 plus N2 plus N3, means number of moles of component up to I, or you can write it like this also, Ni by summation of Ni. All right, so here also sum of the mole fraction will be unity. Okay, so this was all about the mole fraction. In this chapter we will use this mole fraction very frequently. All right, this mole fraction is very useful. This mole fraction unit is very useful in relating some physical properties of solution. All right, now the vapor pressure, for example, the vapor pressure with the concentration of the solution, it is also useful in describing the calculation involving gas mixtures. All right, okay, now moving on, the next term is molarity. So you have already studied about molarity and molality in standard 11th, so this is basically a revision. So molarity, as you know, that it is defined as number of moles of solute divided by, or you can say dissolved in 1 liter or 1 cubic decimeter of the solution. Okay, fine. So molarity, it varies with temperature due to change in volume of the solution. Always remember, molarity varies with temperature. Okay, the unit of molarity is gram mole per liters, all right, or mole per liter. Okay, now if we are talking, if we just give an example that 0.25 mole per liter or 0.25 molar solution of NaOH, it means that 0.25 moles, or you can say 10 gram of NaOH has been dissolved in 1 liter of water, Okay, so this was all about molarity. The last concentration term is molality. Okay, molality, denoted by small m. Molality is denoted by capital M. Okay, molality is denoted by small m. Now it is defined as number of moles of solute divided by mass of solvent in kg, or 1000 gram, you can rather say. For example, that if 1.00 mole per kg solution of KCl Okay, it is this much is dissolved in KCl. It means that 1 mole, that is 74.5 gram of KCl, is dissolved in 1 kg of water. 1 kg of water. So molality is independent of temperature. Okay, it does not depends on temperature. It is independent of temperature. All right. So that's all for today's session, students. Have a great day. Thank you.